two projects. In this video, we are going to explain about the project that is real-time TCP packet loss prediction using machine learning. Before getting into the execution, first let us understand what is the project about. So what is congestion and how does this happen? Congestion, it happens when the network is overloaded with too much data. This causes the delays, packet loss, or even complete failure of data transmission. So controlling this congestion is really important because to run network smoothly and to ensure that users they have good experience when they use the internet. We do have some traditional algorithms that are Reno and Cubic which work by reacting to congestion. They only adjust the sending rate after they notice the packet loss. So by the time they realize there is an issue, the damage is already done. More packets need to be transmitted, that is retransmitted. The network gets more crowded and the overall performance drops, which affects the user experience. Nowadays, some newer methods try to handle congestion more proactively by keeping an eye on the things like throughput or delay. The idea is to avoid congestion before even it happens. However, these methods they often depend on certain rules or heuristics that are assumptions to predict the congestion. And these assumptions that are heuristics don't always capture the full picture of what is happening in the network. This means that while they can help, they still might not be perfect for managing the constantly changing conditions of the network. Here, the real challenge is being able to predict congestion before it actually leads to packet loss. The idea is that even if we can anticipate that congestion is about to happen, we can adjust the sending rate proactively instead of waiting for the network to start slowing down or dropping the packets. This would allow the sender to react in time, avoiding the need for retransmissions and reducing the delays that come with the packet loss. To make this prediction, we can use the data that is already available in the TCP connection, things like round trip time, congestion window size, and other network metrics. If we can figure out how to use these variables to predict packet loss in real time, we can improve the performance of the network. It is especially important for popular protocols like Reno and Cubic, which rely on packet loss to gauge the congestion. Being able to predict and avoid this loss could make a big difference in reducing latency, increasing overall efficiency, and improving the user experience. So, the idea behind this project is to propose a system. So, this project proposes machine learning models to predict when packet loss is about to happen. And then it will help in adjusting the sending rate before things go wrong. Normally, TCP algorithms like Reno and Cubic react to congestion after the fact. That is, meaning they wait until packet are lost before they slow down. But with this system, we are trying to be proactive. Here, we gather key information from the networks like round trip time, that is RTT, that is the number of data segments sent, the size of congestion window, that is CWND, and a few other network metrics. These features are pulled from the data collected from Reno and Cubic, two widely used congestion control algorithm. We then use XGBoost model, which is a machine learning model to analyze this data. The cool part is that each model is trained separately for the Reno and Cubic because they behave a bit differently when it comes to managing congestion. So by using this ML models, the system can predict when congestion is about to happen and adjust the sending rate accordingly. This means fewer packets are dropped, there less need for retransmissions, and network run more efficiently overall. In short, it's a smart data-driven way to make sure that loss-based TCP algorithms perform better by anticipating issues before they cause any unnoticeable problems. Moving on to the extension part, to further improve the accuracy, we are incorporating CAD boost, that is categorical boosting model, that uses gradient boosting, which means it builds decision trees iteratively with each new tree improving upon the previous ones. This process allows the algorithm to refine its predictions step by step, making it more accurate over time. As a result, it becomes better at predicting packet loss because it continuously learns and enhances the prediction. Additionally, we have developed front-end using Flask, a web framework, to allow users to interact with the system through an easy-to-use interface. We have also added user authentication that ensures that only authorized users can access the system. This makes the platform more secure and accessible, which provides an effective and user-friendly way to interact with the system. Moving to the implementation part, to implement this project, we have followed the steps mentioned in the flow of. Let's understand what are the steps. So first, the necessary libraries and modules such as Pandas, NumPy, Scikit-learn, and XGBoost are imported to perform data manipulation, machine learning, and visualization. Then comes the data exploration part. So here, two data sets that are Cubic and Reno. Cubic, the data set for Cubic congestion control algorithm is explored to understand its structure and features. Then Reno, similarly, the data set for the Reno congestion control algorithm is explored to understand its characteristics and features. Then comes the data pre-processing part. Here we handle missing values. Missing values in the data set are handled by replacing them with the mean of the respective columns. Then comes the normalizing the data set. The dataset is normalized using standard scaler to ensure all features have similar scale, improving model performance. Coming to visualization, visualizations like pie charts are used to display the distribution of the packet loss labels, that is lost and no lost, for both the cubic and also the Reno datasets. Coming to coming to feature and label preparation here the dataset is split into features, that is input variables, and labels, that is output variables, where the labels represent packet loss. Here we separate labels and features. Coming to shuffling the data, the data set is shuffled to ensure randomness before training. And then irrelevant columns are removed. Any unnecessary or redundant columns are removed to split the model's performance, to improve the model performance. Then comes the splitting the data into train and test. Here, the data is split into two sets. One is training and the other one is testing. Here, 80% of the data set is assigned to train and 20% remaining 20% is assigned to test. So train we use it to train the model, and test we use it to evaluate the model on unseen data set. Then comes the model training part. Here, model, that is the machine learning algorithm XGBoost, is initiated and then trained on the training data set. The model learns patterns in the data to predict the packet loss. Then it is evaluated using accuracy, precision, recall, and FN score, that is to see how the model is performing. Then comes performance comparison through the graphs. So we compare models that are built in this project through the graphs. Coming to front end, here, the front-end interface is developed using Flask framework, which will allow users to interact with the system. It includes user registration and login functionality, which is supported by an SQLite database for storing user information securely. Coming to user input, here in the front end, users they can input the data into the system through the front end, such as network parameters or congestion related details. And that given input is pre-processed, that is normalized and clean to match the format that is expected by the trained model. After that, the pre-processed input is fed with a trained model. So the pre-processed input is passed to the trained machine learning model, which predicts whether packet loss will occur or not based on the input data that is given. Finally, the output will be displayed in the front end whether there is packet loss or not. Moving on to the algorithms used, these are the algorithms used. So here we have used two algorithms, that is XGBoost and CADBoost. XGBoost is trained on both the data sets, that is Cubic and Reno. Similarly, extension model CADBoost is also trained on both the data sets, that is Cubic and Reno. Moving on to the implementation, we need basic requirements to implement this project, that are hardware and software. Coming to hardware, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Coming to software, we need application of Python, front-end framework of Flask, backend framework of Jupyter Notebook, database of SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. This is the overview of the project. Now let us execute. To execute, we need to open the code folder which contains source code files. So let us open it. These are the source code files in the code folder of the project. Let us understand each of them. How will they be used in the project? So let's open the dataset folder. Here are the two datasets that are used in the project, that is Cubic and Reno. Let's open the Cubic folder, that is Cubic file. So this is the dataset that is used to train the models to predict the packet loss. So these are the different features which will influence the packet loss. And here is the target label. Same features we do have in Reno file also. So this is the Reno dataset that is used to train the models for predicting the packet loss. So here if you observe, we have same features, and this is the target label. Now let's close this. And this is the test data file in which we have test cases that we will be using in the front end to predict the packet loss. Let's get back. And this is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files, which are important for the visual appeal. And then comes the templates folder. This folder contains all the HTML pages used in this project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And here we have app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. And this is the Jupyter Notebook file, which contains combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, which makes it a popular choice for the data science. And this is the signup.db file. This file is a database file which is used to store the user information. So this is all about the code folder, that is code folder. Now let's execute. So copy the path of the code folder from the address bar of the file explorer. I'm copying the path. Now open the command prompt. Give the command cd followed by the space and paste the copied path. Now click on enter. Here if you observe, current directory is changed to the code folder's path. Now we are supposed to compile the app.py file by giving the command python space app.py and now click on enter. This command will execute Python script and perform a runtime check for any syntax errors or logical issues. And after running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port unless configured differently. So here it is being loaded. And this is the local host and this is the port. Now we are supposed to copy this local link provided by the Flask framework and paste it in any web browser. I'm copying the link. I prefer Google Chrome, so I will paste it in that. Paste the link here, click on enter. This is the web page of the project which is displayed in the browser and this is developed using Flask framework. Here you can see sign up, right? We need to click on that for getting signed up. Click on that. So enter all the registration details if you are registering newly. I have already registered, so I'll directly sign in. Click on sign in and give your username and the password. So I'm giving my username and the password. Click on sign in. We have signed in successfully and we are redirected to prediction page of the project. And here you can see choose file button, right? We need to click on that for uploading the test case file. So click on that. So this is the file that we are uploading. Before uploading, let's see what do we have in this. Open the data set, open the test data. So these are the inputs that we are going to give now. Let's understand each column. So the first column we have is the expired time. This is the time duration until the packet or the data in a connection expires. It helps in managing the lifetime of the data in transmission process, ensuring that packets are not processed after their expiration time. Then comes the RTT, that is round trip time. It is the time it takes for a packet to travel from sender to the receiver and back. RTT is a key indicator of network delay, where higher values may indicate congestion or network issues. Then comes packet rate, that is packing rate. It is the rate at which data packets are sent over the network, typically measured in packets per second. It is crucial for understanding how fast it is being transmitted and that can indicate potential network congestion. Then we have is CWND, that is congestion window. It is the size of the congestion window which controls how many packets can be sent before waiting for an acknowledgement. A larger CWND allows more packets to be sent, while a smaller CWND indicates network congestion. Then we have is SSTHRESH, that is slow start threshold. The threshold value used to transition between the slow start phase and the congestion avoidance phase in TCP. It helps in adjusting the transmission rate to avoid congestion where packet loss is detected. Then we have is data SEGS sent, that is segment sent. It is the total number of data segments or the packets that have been sent from the sender. This helps cracking the volume of data being transmitted over the network. And the last feature we have is CWND diff. That is nothing but congestion window difference. It is the difference between current value of congestion window and its previous value. This metric helps to assess how quickly the sender is increasing or decreasing the window size, which can indicate network conditions or congestion events. So based on these features only, loss will be predicted, whether there is packet loss or not. Based on this data only, we will be predicting. So this is one case. This is the second case. Third case, similarly, we have all these cases. Now let's close this, get back to the application, select it, click on open. It has been loaded. Now click on upload. So this given input will be pre-processed at the backend and then it will be feeded with the train model. After feeding it with the train model will be giving us a prediction. So this is the first case which we have uploaded. So these are the different feature values in the first case. And here we have prediction of packet loss as false, which means there is no packet loss. Similarly, the second one we have is the prediction as false. That means there is no packet loss. So here, these are the features. For this features, it has predicted as this. And for the given next transaction, it has predicted as true, which means there is packet loss. That means there is delay. And here similarly for all the other features, it has been given the prediction. So in this way, you can give n number of cases for predicting. Now let's check with the graphs. Click on graph. So here, the first graph which we have is the confusion matrix graph of the extension model. So this is the confusion matrix graph of extension model. And this is the extension model CAD boost with the Renault model, that is Renault dataset ROC AUC curve graph. Here on x-axis we have false positive rate and on y-axis we have true positive rate. And this is the accuracy score comparison graph. Here on x-axis we have accuracy score and on y-axis we have all the algorithm names. So these are the algorithms trained on both the data sets. And here we have precision score comparison graph. This is the recall score and this is F1 score. Now click on sign out. And this is all about the project.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.